Lesson 44, altering reaction rates. So this is all about how we will be able to explain how chemical reaction rates can be changed. Now, I'm going to be honest with you guys with these slides. There are 4 ways to change chemical reaction rates. And I was working on some slides to make them look, the slides look really, really good. But unfortunately, I didn't get a chance to finish all of the slides. So I'm probably going to, I've done 2 of them, 2 of the main ways, and I'm probably going to talk about the other 2, maybe using some pictures on some paper and just sort of try and get you guys to see what's happening. But we're going to, before we start, we'll go quickly back and have a look at what we did last lesson. Last lesson, we talked about leading into this lesson, which is speed of a reaction. We said some reactions occur very, very quickly, and some reactions can occur very, very slowly and take a very, very long time to work. We said that in order to get a reaction going, you need 2 things. You need to have enough energy to get them started, so an activation energy, but you also need enough reactants to keep the reaction going. You need to keep supplying them with reactants. So that's how you start a reaction. So for example, carbon plus oxygen goes to make carbon dioxide. To start a fire, you need 2 things. You need spark, which is an activation energy, and you need wood or oxygen to keep that reaction going. That's the reactant. Now, at a particle level, though, when we look at things, is that we want to know if you've got enough activation energy for them to break the bonds between them, and also are they orientated the right way? Because if they weren't orientated the right way, they wouldn't actually react. So the main thing, and I'm actually going to bring this up again, is increasing the number of collisions or ensuring the orientation is correct will speed up a reaction. And that's exactly what I'm about to re-explain to you guys. But before I do that, we'll quickly say the 4 ways of changing the reaction rate. Sometimes they refer to 5 ways because they break this top one up, but because I'm trying to simplify with you guys, I'm going to stick to 4. The 4 ways are the concentration or the amount of reactant, which is what we just sort of said before. We said, we said back here, make sure there's enough reactants. The second way is changing the temperature. The third way is the surface area, or the 4th way is to use a catalyst. I'm going to try and talk about each of these, not necessarily in this order, but yeah, I'm going to talk about them, and then I'm going to show you as we go. I'm going to show you some animations and stuff on style, because style's done a really good job in this section of really going through the animations and trying to show students what's going on without a teacher, without you guys necessarily needing a teacher. So it should help you guys, it should explain bits and pieces as we go too. So let's talk first about temperature. Before we do that, the particle level. So this is pretty much the same slide as before, but I've changed it a little bit. So what's needed to make a reaction is, it needs to have enough energy per particle. So you need to have enough energy to break the bonds and form new bonds. That's the whole reason that you have activation energy. If you have a really, really, really cold liquid and you're trying to get 2 chemicals to react, you probably won't react because it's probably too cold. So you need to make sure that each particle has enough energy. But they also need to have the correct orientation. Now, there are some shortcuts to making a chemical reaction work. And these are the shortcuts that we're going to use the most. More collisions. So if you've got 1 particle colliding, great, cool. If you have 20 particles colliding, then at least, it's more likely to happen. More collisions means more chance of correct orientations or correct energy. Let's just say randomly, let's just pull a random number out. I'm going to give you guys a second to copy this down, but I'm going to talk for a little bit. Let's just say a chemical reaction. Let's say that when 2 particles crash into each other, the probability that they will react the probability that these two particles react when they crash into each other, let's call that 50%. So there's a 50% chance that when they react, they will make, they'll make a new molecule. There's also, let's just say, a 50% chance that when they react, then there will be, that'll be it. They'll just fly off. They'll bounce off each other. So that means that the best way to increase the reaction rate is to ensure that you've got more collisions happening. If you have 10 collisions and you expect 5, you'd expect 5 products. But if you have like 100 collisions, then you would expect 50 products. So the best way to ensure that you that a chemical reaction will work is to have more and more collisions. You could also, if you made these guys move faster and crash into each other more often, you could also increase the amount of collisions without increasing the amount of chemicals. But we're going to talk about how these all work in the next couple of slides. But just getting the basics, more collisions means more reaction is the basics here that I would love you guys to grab. I'm going to change the slide unless anyone yells no. And we're going to look at the very first of our 4 methods, which is temperature. Temperature. Now, temperature, in my opinion, Style has chosen to start with temperature. I hate starting with temperature. Personally, I think temperature is the most confusing of all the ways to increase reaction rates because it does it in 2 ways. But, let's talk about it anyway. If you increase the temperature of reaction, what does it mean? A higher temperature means particles move faster. That is the very first thing. Particles will move around a lot faster in a higher temperature chamber compared to a lower temperature chamber. And this is actually a good thing because if you increase the temperature, this is a good thing because what it does is particles have a greater energy. So the particles, they're flying around, they've got a lot more energy. So when they collide, they're more likely to break the bonds and form new bonds. So, so that means is that, okay, so because you could have 2 things colliding and, they don't form new bonds. So therefore you haven't got a new chemical, a new molecule. But if you have, if they're moving really quickly, then you've got a lot of energy, they're more likely to form new bonds. The second thing is, if they're moving quicker, they're more likely to collide. Because if you're moving faster, then you have less chance to avoid where you're going, you have more chance to just bash into something. So that's why we say there's more chance for you to collide with something. So that's why we say moving faster means they're more likely to collide. And so both of these methods will increase the reaction rate.
Yo, Mr. Greer.
Yo.
Can you explain? So like, if you're like in water and it's like freezing cold, what happens to your body? Like, what happens to it?
I'll quickly, but it's sort of not really. I can see why you're thinking that. You're thinking cold, and I can get that. But yeah, it's sort of applicable, but it's not super applicable because what happens when you get cold, you start to shiver, and you start to shiver because your body's trying to increase. You start to shiver because your body's trying to increase your temperature, and that's why. That's sort of why you shiver, is because you're trying to move your muscles and contract your muscles to make yourself warm. And yeah, a lot of other things happen in your body in a way to try to conserve body heat. Because if you get too cold, then a lot of your muscles, a lot of the chemicals in your body don't work anymore. How can I relate this back to what we're talking about? One of the reasons why we use a refrigerator to keep our food cool is to stop it from going bad. And if you keep your food cool, it lowers the reaction rate. It lowers the reaction rate because it makes the particles move slower, so they have less energy and there's less likely to collide. So therefore, if you've just bought some fish and you don't want the fish to go bad, if you put it in the fridge or you put it in the freezer, the particles in it will be moving a lot slower, so they're less likely to react and make, gases that smell bad and stuff like that. So that's why you would put things in a fridge. I know I've sort of taken your question, Brendan, and changed it back, but I'm trying to direct people back to this idea here. At the top here, I've got a pitch. At the top here, I've got two examples here. This one on the top is meant to be hot, and this one on the bottom is going to be cold. Now, let's watch and I made this. This is a problem. I spent a bit too much time on this, and it's actually not a very good picture, but I thought I'd go through with it anyway. So this top one, right? If you look, the particles move around really quickly. And because they're moving around really quickly, there's more likely to crash into another particle. And in fact, you do get a reaction happening down the bottom. Because these two particles crashed into each other, they made a reactant. Whereas in the cold example, the particles are moving around a lot slower. And therefore, they just, if you look here, these two down here just crashed into each other, but because they're moving so slowly, they don't actually react. So that's the two things, is that because they're moving slowly, there are less collisions. But because they're moving slowly, there's less energy. There are two reasons why increasing the temperature increases the reaction rate. So now what I'm going to do is I'm going to jump over to style. And the reason I'm going to go to style is because style has got a really good animation for this. So if I go over to style, and the other reason as well is it gives me a chance to show you guys what you're going to have to do when I set this for you guys to work on. So I'm going to set this probably at the end of the lesson for you to work on. So if I scroll down here, these are 3 of the methods that we're going to talk about. I'm definitely going to talk to you guys about these first 2 today. Maybe talk about this third one. I haven't decided yet. So there's a video here, and what they do is they talk about glow sticks. They put a glow stick in cold water or a glow stick in warm water. And they sort of see what the difference is. They said that light's released during the chemical reaction. But the one that I wanted to get to is, this is the part, I guess, if I skip this here. So you watch, right? Initially, they're both the same color because they're both, and then as time goes on, this reaction, because it's hot, reacts really, really quickly, but then, and the cold reaction reacts really, really slowly. So this reacts quickly, emits a lot of light, but then as time goes on, you can sort of see that the hot one has reacted really quickly and now it's finished the reaction. There's nothing left. It's sort of not glowing as much. Whereas the cold one is still glowing a lot. And that's because its reaction is really, really slow. So it's still got some light coming out of it. If you don't believe me, you're like, oh, those look the same, sir. What they did is they moved the sticks side by side. And then you can sort of see, yeah, the cold one is a little bit brighter. I would have left it a bit longer if I was doing this chemical reaction just to make it a bit clearer, but yeah. What I wanted to get to was this here. This is a great example of what's happening. So what we're going to do is this is a better animation than the animation that I just did. But we've got 2 reactants. We've got a blue and a yellow one, and they react to make a blue-yellow. So what we're going to do is we're going to start off by having our temperature really low. I'm going to see how long it takes for all of this blue to be reacted. So if we watch, right? All right, yeah, it's reacting. It's going to take a while. Why is it taking so long? Because these things are moving very quickly. So they're not like, some of them aren't even like reacting. They're just sort of going near it. And even if they are, like, a lot of them are moving very slowly. I'm just watching this one right here. slowly moving. The other ones as well. Some of them are moving a bit quicker, but yeah. And if you look, it's going to take a while before they react. I think they've sort of ignored one of the ideas, which is just they've just sort of assumed that every time they touch, there's a reaction. But in reality, you could bang into one of these and not actually get a reaction happening at all. I'm going to give this another 5 seconds, and then I'm going to stop. That's going to take forever. But you saw how long that took. Well, let's crank up the temperature. We crank up the temperature, we reset. Now these particles are going to be moving faster. Faster particles, more collisions. More collisions, that means that the reaction is going to happen faster. There are a lot more of these blue floating particles now because that reaction is happening really, really quickly. The other thing as well is that when they collide, they're more likely to react, because if you collide, yep, you're going to react 100%. And so it keeps going and it keeps going. And I'm going to give this maybe, I'm sure I might give it a minute because I gave the other one a minute. These, you can also tell there are still some slow particles in there, but most of them are pretty quick. These are designed as well. Once they react, they stay in there. So there's less and less and less particles to react afterwards. So if you now compare, if you're comparing things, if you compare this one with the one that happened before, the reaction happened a lot quicker. Let's crank up the temperature one more time. Let's turn it up really hot. This is now really hot. The particles are moving really quickly. And because of that, you can see how quickly this blue, like whatever it is, maybe it's a sugar cube, whatever it is quickly disappearing. It's because there are just so many collisions happening. And that's because the particles are moving so quickly that they're just able to like collide and move around a lot faster. And yeah, it's going to be, give it a little bit longer, I'll give it maybe a minute, but you should be seeing quite clearly now that they're going away quite quickly. I might stop it about there just because the reactions slow down. The reason reactions slow down at the end is because there's less reactants. Okay, notice that there's only like a couple of reactants here. And even though like those reactants are moving really quickly, because there's less of them, they just don't react very often. So that's temperature. A little bit more. I will quickly show you with this. Then it's got some questions, but it's got the same thing here. I want you to plot a graph. I wanted to show you guys what that graph would look like. And then I guess I'm going to wrap up pretty much the end of temperature. So how you can set this up is you set one to work at low, one to work at medium, and one to work at high. And then I want you to plot a graph. I couldn't get this to work last night because I was like, because I was just, I just couldn't figure it out. But I think what you do is you go 5, 10, 15, 20, 25, and you got to do, it's going to take you a little bit of time to do. And this is going to be we'll call this one the hot one, call this one the medium one, we'll call this one here the cool one. And how you do this, this one is you set it, you let it go for 5 seconds. 1, 2, 3, 4, 5. And then you record the amount. So for the cold one, or we'll change it around, but it doesn't matter. There's 15, 20, 38. So go 15, 20, 38. And so that gives you you can then sort of use this to plot what's going to happen. And you're only supposed to do this for 30 seconds. So you're not supposed to do this all the way. Okay, 23, 44, 60. So 23, 44, 60. And then I'll do one more with you guys, but just so I can show you. This is how quick it is. I've already gone 35, 58, 68, 35, 68, 35, 58, 68. And then the reason why these aren't plotting is because I haven't done this. 10, 15, 10, 15. And so, yeah, what you will be able to see is you should be able to see that this one will curve up, but then it will sort of flatline. And the reason that they go flat, I'll show you down here. Where is it? The reason they go flat is because they run out of reactants. So when they run out of reactants, they can't keep reacting. This steeper slope, I will give you the answer here. Because it's steeper, it's reacting faster. It's making these products a lot faster. So we say that its reaction rate is faster, so it must be a hotter temperature. Whereas this one is reacting slower. So it's not as reacting as fast, so therefore it's got a lower temperature. So anyway, that's how you do that. And I'm actually going to set this for you guys to do afterwards. So and I'll probably get you guys to do that. I might only do 2. I think I'm only going to do 2 this lesson. I think I'm going to do temperature. And then I think I'm going to do this next one, which is going to be surface area. Because they're the only 2 that I've created images for. But we'll talk about that. So now let's go back to the PowerPoint. I'm going to talk to you guys about, and I would like you to jot down this one for the next idea. Surface area. Okay. Now, surface area is probably one of those things that you've seen in maths a few times, but in science, we're going to talk about it now just to get a bit of an idea of what's going on. By increasing the surface area, there are more places for reaction to take place. Now, more places for reaction to occur. Now, if there's more places for a reaction to occur, that means there are more reactants to react. And of course, whenever you have more reactants to react, that means there's going to be more collisions, so more reaction. You want to get as many reactants reacting as possible. So this will increase the rate of reaction. The simplest way to increase the rate of reaction, to increase the surface area, is by breaking a reactant into smaller pieces. So there are other ways as well, of course. One way as well to further increase the reaction rate would be, of course, to talk about stirring. A lot of you guys will hear was like, oh, stirring. You think, yeah. So if you just dump a bunch of solid into a chemical reaction, it's probably not going to react. It's probably just going to sink down to the bottom and do nothing. So when you stir, you're introducing more particles into a chemical reaction, or when you shake it, so there's more likely for those particles to react because new surfaces are appearing for them to react on. So let's grab a look at this big, I don't know what you want to call it. You can call it an ice cube, call it a sugar cube, you could call it copper sulfate. I don't care what it is. We're going to look at this. We're going to say, well, it's got, on the copper sulfate, it's got whatever it is. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 locations to react. So if I was a chemical, and I was coming in, I could react here and form a new product. If I react here. But hopefully you guys can see there's a bit of a problem, right? This little whatever it is, this little copper sulfate atom or molecule or whatever you want in the middle of this big cube can't react with anything. Okay, it can't react with anything because there's no surface area for it to react. The particles just couldn't get, like if I had a particle here and I'm going to react it with this middle one, I can't get to it. I can react with this outer one, but I can't react with this inner one. So what I have is I've got wasted reactant. Right? I've got a reaction, I've got wasted reaction here. I have to wait for all these other ones around the edges. I have to wait for all of these ones to react before I can react with this middle one. So I've got a wasted reactant here. So how can we fix this issue? Well, you can fix this issue by breaking it up. Okay? Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you believe me, there are 24 locations to react. I've doubled the locations that I could react on by cutting this into thirds. Now this one in the middle, he's like, at this point now, he's like, you know, he's a bit happier because now if you've got a chemical that comes along, it can react with this one in the middle. But there's still two sides that it can't react on. Whereas these ones in the end, they've got 3 sides they can react on. This one's only got 2. So it's less likely to react with this middle one. We can make it even more likely to react if we break it up even further. So let's do that. Let's break it up a little bit more. We break it up, and then we've got all of those. So now we've got 36 locations to react. And so now this middle one and this middle copper sulfate atom or molecule, whatever it is, it's a lot happier because now it has 4 places that it can react. And therefore, because there's 4 places, it's more likely to react. So, yeah, the lesson here that I would really love you guys to understand is that in order to increase the reaction, you've just got to try and increase the surface area, create more space for it to react. This can be done by breaking up the chemical. It can be done by stirring the chemical to make sure that more of it's in contact with the liquid. It could be done by creating certain types of structures that allow them to react. If you ever get the chance to look inside a muffler or of a car, what it has is it has a grid pattern. The reason it has a grid pattern is because it's got a lot of surfaces for a reactant to come in contact with it. You want to have lots and lots of surfaces. And so that's why that other picture I showed you with the, if I go back to here, this powdered sugar dissolves in your tongue because it's so powdery and small. That's why they put it on donuts. But they don't put like granulated sugar on donuts because that would be crunchy, and so it wouldn't dissolve easily. You'd have to break it up with your teeth. In fact, that's one of the main jobs of your teeth, is to break up, you know, food into larger surface areas so that you can eat it properly. Your teeth is, you know, if you like, don't get me wrong, you could swallow a whole, like, I don't know, peanut or whatever. You could swallow a whole peanut and your body would be able to deal with it. But it's easier for the body if you break it up into smaller particles, because then your body can dissolve it a lot easier. Your stomach can dissolve it a lot easier. It's called mechanical digestion. That's the whole point of one of the main points of your mouth is to try and do that kind of thing. Another example of this is burning firewood. I always go back to firewood because I feel like it's a chemical reaction. You guys can also be like, yeah, sure, that makes sense. So you can't really start a fire with just firewood because it's too big. I've done my fair share of time of seeing students go, oh, here's 3 big logs, great, cool, fire up the start. It's like, well, I haven't seen many students. I've seen people do it, and they're like, no, you can't do that. You can't even use kindling. You've got to start at tinder, so very, very small pieces of paper or wool or small sticks. Get a fire going with that first, then use that to burn the kindling. The reason the tinder burns so well is because it's got such a high surface area. You can literally get like pieces of like bark that's really, really stringy. And each string has just as much surface area as a piece of kindling. And so therefore it's like trying to burn hundreds of tiny, tiny sticks at once. And that's why it burns so quickly. And then you use that quick reaction to burn other things. So now, let's jump into the style. We'll see what style if style's got any cool animations on this as well. So this is the surface area one. I wonder if I go like this, how it will work. So if I go down here, it's going to talk about, in this case, I think it's going to talk about.
In this demonstration,
I think they're going to try and dissolve a tablet in one, and then I think the powder of that tablet. So taking the tablet and crushed it. So with crushed tablet should react faster. Make your prediction. Which one's going to react, the crushed tablet or the solid one? I'll let you guys make your own prediction. Actually, I could get you guys to do that now. And then what it does is it goes into talking about the rest of it. They've got a bit of, oh, what's this?
What is surface area?
I think this is the same sort of thing that I just showed you. So they go, okay, you got 4 boxes, and so then they break the boxes up, and you got new surfaces. I wonder if that's automatic, or I think that might be a cool little device. I think it might be, yeah, that's cool. It's actually, I think that might be a device, it might be a computer animation, I can't tell. But yeah, it doesn't matter. I think it's a computer animation. I'm an idiot, but that's fine. And so then it talks about this. Here's the image that I wanted to show you guys. We're going to do 3 things. We're going to talk about low surface area here. We're going to talk about medium surface area here. Same amount of particles, but now they're broken up. We're going to talk about high surface area here. Same amount of particles, except they're broken up. Now, if I start this reaction, make a prediction, which one's going to go the fastest? Here we go. Same temperature, by the way. So if you look at this, that purple one is going pretty quick. Whereas this green one here is going very slowly. These middle ones, they can't react until the outer ones are done. But for these, same for this middle one here, but for this one here, the purple one, they're pretty much all gone. So once they're all gone, you reach almost 100%, it's pretty much done. This orange one is going, but it's going to take a little bit of time, but eventually it's going to get done. And this green one's also getting close to being completed, but it's taking a long time. But if we just look at the very, very start, this purple one shot up. It reacted really quickly. The orange one reacted okay, but the green one took a very long time to react. And so that's how surface area works. And then there's another example. You got some sodium azide, which is actually the stuff in airbags. I think they talk about how quickly does it produce gas based on pellet size. So which of these ones is the best?